Welcome to Everyday Mathematics. As we always say here at Everyday Mathematics, we do enjoy solving the harder problems, but above all, we do also see and appreciate the beauty in the simpler problems. So today our problem of interest is from the MIT 2023 Integration B, the finals. The problem of focus today is problem 5. This is a very hard problem, and I'd like to encourage those of you who have or need a cup of tea to get that cup of tea ready. But I hope you do enjoy the two solutions that we're proposing today. The first solution is a harder solution. The second solution is a more intuitive one. But both solutions are very beautiful. So it is our utmost pleasure to share with you the solution today. So before I jump into the solution, I'd like to thank our subscribers. Thank you so much for the support, and thank you so much for viewing and watching our videos. For our first-time visitors here at Everyday Mathematics, what we do is we seek for harder problems, and then we try and solve them and share with you the solutions. So if you're inclined, please pause the video and press on the subscribe button. You could also press on this notification button to get regular notifications whenever we upload a video. For our repeating visitors who have not yet subscribed, we do encourage you to subscribe to our channel. So the problem today is the integral from x equals to 0 to x equals to 1 of the summation from n equals to 1 to infinity of the floor function of 2 to the power n x over 3 to the power n close bracket squared. So very, very intricate problem, but let's see how we could solve it. So how I would approach it is, first, I would want to expand that summation sign a little bit. And how I would do that is, as you can see here, we have floor function of 2x over 3, floor function of 2 squared over 3 squared, plus floor function of 2 cube x over 3 cube, plus on and on and on. And then we would square that as our integrand. And so what that results into is we would have the quadratic components, which results from squaring these respective values. So we would have the floor function of 2x over 3 squared, floor function of 2 squared x over 3 squared, floor function of 2 to the power 3x over 3 cube squared, and so on and so on. So the quadratic function would remain. Then we would have the terms that result from cross multiplying the terms. So for example, we would have, because each multiplication will go twice when, for example, when you're multiplying 2x times 2 to the power 2x, the floor function of those, and then when you're considering the multiplication of 2 to the power 2 floor function x as the principal multiplier. And so essentially the cross multiplication of these independent terms would happen twice. And so we have plus twice when 2 is the principal multiplier, and then and so on and so on. And then we add 2 when 2 to the power 2x is our principal multiplier there. And as you go on and go on and go on. And so the fact that we've already accounted for floor function of 2x and 2 to the power squared x, we won't repeat that. So we'll begin from 2 squared x, and then we go to times 2 to the power 3 floor function x, and so on and so on. And so that when we go to the next level, plus 2, 2 to the power 3x floor function with the next higher value to the power 4x, and so on and so on. So this kind of trend will continue. And so we can now divide this into the quadratic integration, the integration of the quadratic terms, plus twice the integration of these cross terms, okay? The summation of the cross terms. Obviously, these quadratic terms can also be expressed in a more succinct manner. As highlighted by the blue integration. So we would have the numerator and the denominator considered separately. I would also like to now, since we independently considered floor function of 2x as a principal multiplier, floor function 2x times to the power 3, I would like to flip that so that in this, the column direction is where we're focusing on the 2 as the principal, the 2x floor function as the principal multiplier. Okay. As we continue, let's focus on the blue, the quadratic terms, or the squared terms. So the square of the floor function of 2x over 3 is the same as a floor function of 2x squared over 3 squared. And then obviously plus the floor function of 2 squared x squared over, now the 3 squared here, squared, it becomes 3 to the power 4. Now how we can visualize this is that what a floor function essentially is a discretization function that curves out, or that gives you the integer lower than the real number you're looking at. For example, if we are looking at, for example, 2 floor function 2x squared, that means that, and if the domain of interest is 0 to 1, that means from 0 to half, the lower integer is 0, and so 0 squared is going to be 0. And then from the interval 1 over 2 to 1, we have 1, and so the floor function 2x squared in the interval half to 1 will be 1 squared. If, for example, we look at the floor function of 2 squared x, which is the same as floor function of 4x, so we have to divide the interval 0 to 1 into 4 sub-intervals, such that from 0 to a quarter, 2 squared x is 0. So in other words, 0 squared will be 0. From a quarter to a half, that would mean that it will be 2 squared x will be 1, and therefore 2 squared x floor function squared is equals to 1 squared. From a half to 3 quarters, it will be 2 squared x floor function will be 2, and so that squared will be 2 squared. And so from 3/4 to 1, the floor function value will be 3. And so the square of that will be 3 squared, right? So that's how you would look at it. So now at 1, obviously, 1 times 2 squared is 4, so it will be 4. But that is just that instantaneous value at that particular point of x equals to 1. So we won't really factor that. And so the integration of these subcomponents, for example, of 2 squared x floor function squared over 3 squared If we focus on the numerator alone, so the integration will pretty much just be the area under this curve. So from half to 1 will be pretty much the area of the rectangle. So the width will be half and the height would, or the length would be 1 squared. And obviously we would now, if we are to consider the entire fraction, it will be this 1 squared over 3 squared times a half. And then for the 2 squared x squared, the integration from 0 to 1 would be the integration or the area of these rectangles. And that would be, for example, 1 squared over 3 to the power 4 times a quarter plus, here is 2 squared over 3 over 4 over, times a quarter. And this strip has the same width, so it will be 3 squared over 3 over 4 times a quarter. So summing up all the strips, the area of the strips. And that's how you would go about finding the area of these floor functions. So to express it in a more easy to comprehend fashion is for 2x floor function squared, we had only 1 squared times 1 over 2 or half, and then for over 3 squared, and then for 2 squared x floor function squared, we have 1 squared plus 2 squared plus 3 squared times 1 over 2 squared over 3 over 4, and then for floor function of 2 over 3x, to the power 3x squared will be 1 squared plus 2 squared plus so on up to 7 squared times 1 over 2 to the power 3 times 1 over 2 to the power 3 over 3 to the power 6. So that's how you would go ahead. So in a more general way, you would say that this is, for the first one, we would have 1 over 2 to the power 1 times the summation from k equals to 0 to 2 to the power 1 minus 1, k squared over 3 to the power 1 squared, plus 1 over 2 squared times the summation from k equals to 0 to 2 to the power 2 minus 1 k squared over 3 to the power 2 squared, plus 1 over 2 to the power 3 times the summation from k equals to 0 to 2 to the power 3 minus 1 k squared. So since this is 7 and this is 3 and this is 1, so this over 3 to the power 3 to the power squared, to the power 2, sorry. So, and then since we know that essentially when you're summing up something k squared up to n, this is the same as n over 6 times n plus 1, n plus 1 times 2n plus 1, right? And that's what we've gone ahead to use, this formula. Our n for this is 2 to the power 1 minus 1. So that's what we included here. So 2 to the power 1 minus 1 is our n. 2 to the n plus 1 is 2 to the power 1 minus 1 plus 1. So we have 2 to the power 1. And then here 2 times 2 to the power 1 minus 1, which is now 2 to the power 2 times 2 to the power 1 minus 2 plus 1. And we get this 2 to the power 1 plus 1 minus 1. And we've repeated that accordingly, right? And so what we eventually get is that we do have a general summation from n is equals to 1 to infinity of 1 over 2 to the power n times 2 to the power n, right, times 2 to the power n minus 1 times 2 to the power n plus 1 minus 1 over 6 over 3 to the power n squared. So this will give us, if we compute this sum, this will give us the summation of the quadratic terms, the squared terms of our integration. So since this would cancel with that, we are left with 2 to the power n minus 1 times 2 to the power n plus 1 minus 1 over 6 over 3 squared to the power n. And so we can pull a 6 out, and so we have 2 to the power n minus 1 times 2 to the power n plus 1 minus 1 over 9 to the power n, right? So pulling, as we said, we pulled a 6th out, and so now we can multiply across 2 to the power n times 2 to the power n plus 1. We have 2 to the power 2n plus 1 minus 2n minus 2n plus 1. 1 times negative 1 is a positive 1 over 9 to the power n. And so pulling a 6th out, we have 2 to the power 2n plus 1 minus 3 times 2 to the power n, because this is twice to the power n, and then we have plus 1 over 9 to the power n. So pulling a 6th out and dividing across by 9, so this 1 here results into 2 here as our constant, and then we have 2 squared over n, to the power n over 9 at the power n. So in bracket, we have 2 squared over 9 minus 3 times 2 to the power 9. That's to the power n, 2 over 9, the power n, plus 1 over 9 to the power n. And so these are geometric series with 1, the initial value being, for here we have 2 squared over 9. The initial value is 2 over 9. The initial value is 1 over 9. And then the constant ratios are pretty much the same value. So we have now 1 over 6. So we just expanded 2 squared to 4 over 9. And so we have 4 over 9 as a common ratio, 2 over 9 common ratio, 1 over 9 common ratio, and the initial values are pretty much the same values. And so when we end up solving this, is now we have 1 over 6 in bracket, 2, initial value, 4 over 9 minus 1, divided by 1 minus 4 over 9, which is the common ratio, minus 3, 2 over 9 initial value over 1 minus the common ratio 2 over 9 plus initial value 1 over 9 over 1 minus common ratio 1 over 9. So 1 over 6 times 2 times 4 over 9. 1 minus 4 over 9 is 5 over 9 minus here 3, 2 over 9 over 1 minus 2 over 9 is 7 over 9 plus 1 over 9 over 1 minus 1 over 9 is 8 over 9. So essentially these guys would cancel, these guys would cancel, these guys would cancel, and these guys would cancel. And so we're left with now 1 over 6 times, in bracket 2 times 4 over 5 minus 3 times 2 over 7 plus 1 over 8. And so as we continue, we can now multiply 2 by 4, we get 8 over 5 minus 6 over 7. 3 times 2 is 6 over 7 plus 1 over 8. And then common denominator here is 280. 280 divided by 5, we get 56. 56 times 8, 448 minus 280 divided by 7 is 40. 40 times 6 is 240 plus 280 divided by 8 is 35. 35 times 1 is 35. And so when you compute this further, this becomes 243 over 6 times 280. And so 6 divided by 3 is 2. 6 divided by 3 is 81. And so we have 81 over 560. So 81 over 560 is the sum of the square terms or the quadratic terms. Now we do have the green integrals to work on, and that is the cross terms. So the green terms is fascinating, since we had shuffled the rows and the columns. So if we look at this 2x floor function times 2 squared x floor function, diagrammatically, what that really means is that the floor function of 2x is that if we divide the interval 0 to 1 into 4 sub-intervals, that means from 0 to a half, the value of floor function of 2x is 0. And from half to 1, the value of the floor function of 2x is 1. And then we're multiplying that by the, for example, 2 squared x floor function. And that means is if we divide the strip into the 4 sub-intervals demanded by this 2 squared here, into 0 to a quarter, quarter to a half, half to 3/4, and 3/4 to 1. That means from 0 to a quarter, 2 squared x floor function is 0. From a quarter to a half, the value of the 2 squared x is 1. And from half to 3/4, the value of that floor function is 2. And from 3/4 to a half, the floor function value is 3. And obviously at 1, it's 4. So multiplying this, it means that it's a vector summation where it will be 0 times 0, 0 times 1, and then from half we have 1 times 2, and then 1 times 3, right? So we can express that summation into a beautiful vector expression. And that will be for the floor function of 2x will be 0, 0, 1, 1 times 0, 1, 2, 3, and then times 1 over 2 squared times the 1 over 3 cubed, which is 3 times 3 squared. And you continue again 0, 0 up to 3 dot. This is the dot product of 0, 1 up to 7, and so on and so on. So this is a beautiful dot product problem. And we're going to slowly show how we can use general expressions of summation to actually obtain these values. You don't need a program or a computer to solve this. You could use this by pen and paper. You could solve this by pen and paper. So as we continue, we'll see that since we have here 3 times 3 squared to the power 1, and then this 2 squared is the same as 2 times 2 to the power 1, and then we are summing up. What I've decided to do is split it into 2 different summations. We have the even and the odd. So we have, for example, if we take k to denote the index of the first from 0 to 1, so we have 0 times 2k, and then k times 2k plus 1. So that is 0 times 0, 0 times 2. I mean 1 times 2. And then 0 times 1, and then 1 times 3. Okay, and you can see this expression can be repeated across the top row. And then as you come to the second row, this 3 here changes to 3 squared. And then this 2 here changes to 4. And then this 2k becomes 4k, because now you have to account for other terms. Now the summation not only factors 2 terms, we are adding all the way up to 4k plus 1 up to 4k plus 3, and we're multiplying by k. All right? And as you continue, we're shifting from 0 to 3, from 1 to 3 to 7, and so on. And we're going to see shortly how this is going to be captured into some form of summation problem. Okay, so if we have that summation captured, we can see that for every row here, we have 3 times h squared, the power n, times 1 over 2 times to the power n, summation of k is equals to 1 to 2n minus 1 times k times 2k, of k times 2k plus k times 2k plus 1, and then we're summing from n equals to 1 to infinity. And the second row, again, as you can see, this 3 here changes to 3 squared, and then this 2 changes to 4, and then this 2k changes to 4k, and then the summation here ends up to 3 instead of 1. And in the succeeding row, we see it shifts from 3 to 7. So we have to find a way of generalizing this summation into something that can be worked on by pen and paper. So we got that. Now we can see that we can add another, we can nest in another summation of j, so that this now becomes 3 to the power j, because this is j equals to 1, j equals 2, j equals to 3. And then this 2, 4, 8 becomes 2 to the power j, so that 2 to the power 1 is 1, to the power 2 is 4, the power 3 is 8. And then since this changes also, we have 2j here. And then since this is 1 is the same as 2j minus 1, 2 to the power 1 minus 1, to the power 2 minus 1, to the power 3 minus 1. So we have summation up to 2j minus 1. So you see now we've created this beautiful nested sums, 3 nested sums, as you can see. And then now, since we have j factored in accordingly, so the next thing is how to express this sum into a nice thing that can be easily summed up. So this is the same as 2jk times 2jk. So we have 2j to the power j times to the power jk squared. And since we have these as, we can use now arithmetic progression, where we say if we are summing up k from 1 to n, this is the same as n over 2 times n plus 1, right? So that's what we've used here. So we see here our n is 2 to the power j minus 1. So n plus 1 is 2 to the power j, and then n is 2j to the power j minus 1 over 2. So we can see this multiplied by k, because there's this initial k plus another k plus another k until k times 2j minus 1. So the sum of those k's becomes 2j times 2 to the power j times 2 to the power j minus 1 over 2 times k. So obviously we can use this to cancel with that, and it can go with that. And now knowing that the summation of k squared to n being equal to n over 6 times n plus 1 times 2n plus 1, we can apply that for this, and we can also use again this for that with respect to 2n minus 1 as our upper limit. As you can see, we have 1 over 3 to the power j times 3 squared to the power n over 1 over 2n to the power j k squared plus 2 to the power j minus 1 over 2 times k. So the k squared term will be summed up accordingly. As you can see, since our n is 2 to the power n minus 1, we have 2n, n plus 1 is the same as 2 to the power n, and then n is 2n, 2 to the power n minus 1, and then 2n plus 1 becomes 2 to the power n plus 1 minus 1 over 6, shown here. And then for the k term, n is 2n to the power n minus 1, and then n plus 1 is 2 to the power n. And so we can again use that to cancel with this 2n and then with this 2n. Okay. So since we've done away with that and with that, and so we're left here with 2 to the power n minus 1 times 2 to the power n plus 1 minus 1 over 6. And then we have 2 to the power n minus 1 over 2 here times 2 to the power j minus 1. And then there's 2 times 2 here, and then there's 6 here. So can go ahead and multiply this out. So we have 2 to the power n times 2 to the power n plus 1 is 2 to the power 2n plus 1 minus 2 to the power n minus 2 to the power n plus 1, and then plus 1 over 6. And then this one remains so, and then 2 times 2 is 4, and then we have 6 here. We can now obviously simplify this further because this is 2 times to the power n, so this becomes minus 3 times to the power n plus 1. The next step is to take this 9. 2 squared the power n, 3 squared the power n is the same as 9, so we want to multiply that across. Okay. So that means that now we have the summation of 1 over 6 times 2 over 3, there's this 2j over 3, the power j in brackets. So we have pulled 2 here, 2 over 2 squared over 9 bracket to the power n minus 3, 3 in bracket 2 over 9 to the power n plus 1 over 9 the power n. And then here we have 2j minus 1 times 4. And then 3j got multiplied across, and 3j, and then we have 2 over 9 to the power n minus 1 over 9 to the power n. Okay, so so we do see that now we do have a geometric progression. We have a common ratio 4 over 9 initial value 4 over 9, common ratio 2 over 9 initial value 2 over 9, common ratio 1 over 9 initial value 1 over 9. Same thing here as well. So we can now have a 6 times 2 over 3 the power j times 2, 4 over 9 over 1 minus 4 over 9 minus 3, 2 over 9 over 1 minus 2 over 9 plus 1 over 9 over 1 minus 1 over 9, 2j minus 1 over 4 times 3j, and then obviously here 2 over 9 over 1 minus 2 over 9 minus 1 over 9 over 1 minus 1 over 9. Okay. So for this arithmetic progression, we have a 6 times 2 over 3 to the power j. 2 times, since this 9 and 9 cancel, we have 8 over 5 here minus 6 over 7 from here, plus 1 over 8, plus 2j minus 1 over 4 times 3j, the power j, 2 over 7 minus a. Okay, so that means that here we do have 448 minus 240 plus 35 over 280. And then here we have 16 minus 7 over 56. Okay. And so we can then get here what we have is 243 over 280. We can now divide this by 2. By 3 is 2, by 3, 81. So we have 81 over 280. And then we multiply 2 times 280, we have, and then this 2 cancel by 2. And so we have, there's a mistake. These 2 won't cancel with that. We just have a 2 here. Okay. So this 9 over 56 comes here, and we have a quarter. And then we are left with obviously 2 over 3j, 2 over 3 to the power j minus 1 over 3 to the power j. So again, this is a geometric progression. And so we can sum it with initial term 2 over 3 and common ratio 2 over 3. And again, here we have the similar thing. We have 2 over 3 initial value minus 1 over 2 over 3, which is our common ratio. 1 over 3 over 1 minus 1 over 3 common ratio. Okay. So as I pointed out, we have 81 over 560 as we calculated here. And we have 2 over 3 minus a third from here. And so this 3 goes. This 3 goes, and 3 goes. So we have 2 minus a half times this, and then 81 over 560 times 2. So we have 81 over 560 times 2 plus a quarter times 9 over 56 times 2 minus a half. So 81 over 560 times 2 plus a quarter times 9 over 56 times 3 over 2. And that becomes 81 over 280 plus 27 over 448. So this is the sum from the cross multiplication. This is the integration of the cross term integrand. And so now if our integration is obviously the sum of the quadratic terms plus these cross terms, then it means now we have 81 over 560 plus twice 81 over 280 plus 227 over 448. Now, obviously, we can now try and find the common lowest common multiple. And we know by multiplying 2 across, we have 162 here, and 27 times 2 is 54. So the LCM there is 2240. And that means that now in the numerator, we have 324 plus 1296 plus 270, which is 1890 over 2,240. The zeros cancel out. We have 189 over 224. And then if we divide across by 9, so if we reduce it further, we get this term 27 over 32. And this is when you divide by 7. So by 7 here, when it's 7, by 7 here, 32. So this is the final answer, which is very interesting. But as you saw, it was a series of very beautiful tracking of the summation steps. Now, in the next solution, it won't be as intricate as we explored in the first solution. So in method 2, the first thing I would do is try to exploit the cyclic or the repetitive nature. And how I would do that is by saying, okay, let me pull out the first term. So when n is equals to 1, we have 2x over 3 plus the summation of n from n equals to 2 to infinity of 2 to the power nx over 3 to the power n and all that squared, right? So this is our integrand. So what that means is that we can now multiply that out. And so there's actually 2 here. So this squared plus 2 times the floor function of 2x over 3 times the summation from n equals to 2 to infinity of 2 to the power, floor function to the power nx over 3 to the power n plus the square of the sum from n equals to infinity of the floor function to the power nx over 3 to the power n. So as we know, with 2 to the power x floor function squared, that will mean it's from 0 to 1, since floor function of 2x is 0, and from half to 1, the floor function is 1, so we have 1 squared. So essentially, the integration would be the area under this rectangle over, obviously, 3 squared. So what we have there is now this here now results into 1 squared over, 1 squared over 3 squared times a half, which is the width. And so this is the area of that, of this, right? And then since we have the 2, we times this. Now, the floor function of 2x is 0 from 0 to a half. And so what that essentially means is that this entire value is 0 from 0 to a half. So the integration is essentially, what happens is it's going to only now straddle from half to 1. So we can express it as 2 over 3, and so the integral from half to 1 of the summation from n equals 2 to infinity of 2 to the power nx over 3n. And the quadratic term remains as shown here. So let's focus on this part here. So what does this mean? This means that since this is open, we can swap the summation and the integral sum, because what this means is we are integrating the sum of subcomponents here, which is the same as the summation of the integral of the independent components. So swapping these signs doesn't really change the answer. So that now if we focus on the integration from 1 over 2 to 1 of the floor function of 2 to the power n x over 3 to the power n, would mean that we can now divide the strips between a half and 1 into, since from 0 to 1 we would have 2 to the power n strips, from half to 1 we'll have 2 to the power n divided by 2. So as you can see, we are beginning from k equals to 2 to the power n over 2 to 2 to the power n minus 1 strip. And in each strip, we have the value of the floor function as a constant of k over 3 to the power n. So integrating that means that we have the summation from n equals to infinity of 1 over 3n from k equals to 2 to the power n over 2 to 2n minus 1. And so the integral is obviously kx with the lower limit k over 2 to the power n. And this really comes from what the floor function essentially is it's equals to k when this actual real number is between k plus 1, or it's less than k plus 1 and greater or equal to k, such that when x is between those two bounds, the flow function is essentially k. And that's what we've done here, right? So the lower limit is k to the power over to the power n. The upper limit is k plus 1 over to the power n. In that interval, everything is k. And so the integration now is kx. So substituting in the limits, we have now k over, since this minus this is 1 over to the power n, and so we have k over 2 to the power n, right? And so we can now pull this out here, and now we can sum the k. So this is an arithmetic progression from k equals to 2n over 2, 2 to the power n over 2 to 2n minus 1. So we have 1 over 18, or 2 to the power 2 over 3, 1 over 3 to the power n times 1 over 2 to the power n. And so the summation here between these is the summation from 1 to 2 to the power. Again, as I said, when you're summing an arithmetic progression up to value of n is the same as n over 2 times n plus 1. So how you can interpret the summation between these two values, you have to sum from 1 to this minus the summation of 1 to this. And that's what we've done here. For the upper term, we have n being 2n minus 1. N plus 1 is just 2n over 2 minus here 2n to the power n divided by 2. So that's the same as 2 to the power n minus 1. And so n would be 2 to the power n minus 1 minus 1. And then n would be 2 to the power n minus 1. And so you subtract these two values to get the value of this summation. Okay, so next thing here, as you can see, we have the summation from n equals 2 to infinity of 1 over 3n to the power n over 1 over 2 to the power n. You can see this and that goes, and this one that goes, because we've lowered one of the 2's from this 2 to the power n, right? And so we have this going, and so our summation becomes 1 over 18 plus 2 over 3 times a half, since we've pulled one of these 2's out. And so we have 2 to the power 1 over 3 to the power n times 2 to the power n minus 1 minus this 2 to the power n minus 1 over 2. So this is 1 over 18 plus 2 over 3 times a half, summation of n is equals to 2 to infinity, or 1 over 2 to the power n. And so this is 2 to the power n minus 1. And so by pulling 2 down from, this is the same as 2 to the power n divided by 2. And that becomes 2 to the power n divided by 4, since we have another 2 divisor there, minus 1 over 2. So we can multiply the 3 to the power n across, 1 over 3 to the power n across. And so we have 2 over 3 times a half, summation of 1 over 3 to the power n. But before that, we could subtract these from this. So we have 3/4 of 2 to the power n minus 1 plus, since this is negative times negative, So negative 1 plus 1 is a negative a half. So this becomes a little bit simpler. So multiply through the power in the denominator across. So we get 1 over 18 plus 1 over 3 times the summation of, into bracket, 3 over 4 or 3/4 of 2 to the power 3, 2 over 3 to the power n minus a half times 1 over 3 to the power n. So these are geometric series. And so we can use the initial term of 2 over 3 squared, which is 4 over 9, minus 1 over 2 over 3, which is the common ratio. And then here the initial term is 1 over 3 squared, which is 1 over 9, minus 1 over 3, which is the 1 over 3 is our common ratio. Obviously, half is kept there. So that becomes 18 plus that times 3/4 times 4 over 9 divided by a third minus 1 over 2 times 1 over 9 divided by 2 over 3. And then obviously we're keeping that as it is. We'll tack that later. So that's 1 over 18. 1 over 3 times 3/4 is 3 divided by 3. This becomes 9 divided by 3 is 3. So we have, anyway, this is 3 and 1. And then this goes with that, and this goes with that. So we have essentially 1 here, and here becomes 3. So we have 2 times 3 times 2, which is 1 minus 1 over 12, because 3 times 4 is that. So we have 1 over 18 plus 1 over 3 times 1 minus 1 over 12, which becomes now 1 over 18 plus a third times 11 over 12. So we finish the first two integrals. Now let's try to see how to attack the third integral. So the third integral is interesting, and the first thing is to try and revert this indexation or the indexing from n equals to 2 to now n equals to 1. So how we do that is by letting n be equal to k plus 1, such that when we plug k plus 1 in place of n, we have k plus 1, k plus 1, k plus 1. And so subtracting 1 on both sides, we are left with k is equals to 1. So our summation now begins from k equals to 1. However, the constants here change appropriately. So we have 3 to the power k plus 1, and here we have 2 plus 1, 2 to the power k plus 1. So the denominator here is easy to handle because we can pull 3 out here, and we are left with 3 to the power k. But whatever is inside the floor function becomes a little bit hard. So this becomes 1 over 18 plus 11 over 36 plus pulling 9 out of the square. So it becomes 1 over 9 times the integral from x equals to 0 to 1 of the square of the summation from k equals to 1 to infinity of the floor function to the power k plus 1, x over 3 to the power k. So interestingly, what happens here is now we have 2 times this. One way to try and remove this 2 times x is by letting u be equal to 2x, and so du dx is 2, and therefore du over 2 is the same as dx. And so when x equals to 0, what u is equals to 0, and when x equals to 1, u is equals to 2. And so our integration now shifts to 1 over 18 plus 11 over 36 plus 1 over 9 times the integral from u equals to 0 to 2 of square of the summation of k is equals to 1 to 2 of floor function of 2 to the power k u over 3 to the power k times du, obviously du over 2. Now this half here can be pulled out here. So now that we have 1 over 18 plus 11 over 36 times we can make this 1 over 18 by pulling 2 there. But now this integrand is similar to what we had initially, but the problem is now our limits now moves from 0 to 2. So we have to divide this integration into two parts. So we have from 0 to 1, and then from 1 to 2. And this we could dub I as our initial integral, and everything on the left-hand side could be I, right? So that is that. So as we said, I is on the left-hand side, 1 over 18 plus 11 over 36 plus 1 over 18 in bracket I plus the integral from 1 to 2 of the square of the summation from k equals to 1 to infinity of 2 to the power ku over 3 to the power k. And this is interesting. Now we want to bring back the limits from 0 to 1. How we do that is by taking things back to x by saying let x be equal to u minus 1. And so essentially u is equal to x plus 1. So dx is equal to du, not changing the variables there. But as you can see, when u is equal to 1, x is equal to 0. And then when u equals to 2, x is equal to 1. And so our integration essentially becomes I is equal to 1 over 18 plus 11 over 36 plus 1 over 18 plus, in bracket I, plus, this integral now shifts. So we have I plus 0 to 1. But in place of u now we have x plus 1, which is now interesting because we can multiply 2 to the power k across. So we have 2 to the power k x plus 2 to the power k. So we know for sure 2 to the power k is an integer. So that means that this is the same as the floor function to the power k x plus 2k. Yeah, or the floor function of 2k. So the floor function of an integer is the same as that same integer, right? The 2k comes out. Now 2k divided by 3k is that extra summation term. So we can now split this into two sums. So the summation of our original variable, but now we have this constant geometric progression of series. So this essentially is obviously a geometric progression of initial value 2 over 3, and then the common ratio is 2 over 3. So we can just do the needful there. And so this is the same as 2 over 3 over 1 minus 2 over 3. So this becomes I is equals 1 over 18 plus 11 over 36 plus 1 over 18 in bracket I plus the integration from 0 to x equals 0 to x equals 1 of the summation of from k equals to 1 to infinity of the floor function of 2 to the power k x over 3k plus 2 over 3 over third. So the 3 is cancelled, so we're left with the 2. And then if you go and do the hard multiplication, so we see that obviously the summation plus 2 here, you square that out, you get the square of the summation from k equals to 1 to infinity of 2kx over 3k plus 4, the summation from k equals to 1 to infinity of 2kx over 3k plus 4, right? So we can now separate this into 3 different integrals. And this here is interesting because now we can swap things, but this is the same as I. So we have 2 i's here, but now we need to solve this. And then this is a trivial integration problem. We have 2i here, and then 4 times, because the sum is the same of the integrals. The integral of sums is equal to the sum of the integrals. So now we can swap these around. So now this is the summation from k equals to 1 to infinity of the integral from 0 to 1 of the floor function of 2k x over 3k, and then 4 times the integral of constant 1 from 0, x equals 0 to 1. So this is easy because now we can split the interval 0 to 1 into 2k minus 1 strips here, and then we can use the index L, and between in each respective strip we have a constant value, and that constant value is L. We've expressed that. So initially we say that if we are thinking of 2k x is equals to L, right? If 2k x is less than L plus 1 and is greater or equal than L, such that L over 2k is less than or equal to x, which is less than L plus 1 over 2 to the power k. Now in this interval, this value is a constant L, and that's what we've done essentially here. But we can integrate, and so we have Lx with the appropriate limits here and here. Applying those limits, we have now 1 over 2 to the power k times L. We can pull 1 over 2 to the power k out here, so we have 4 times the summation from k equals to 1 to infinity, or 1 over 3 to the power k times 1 over 2k summation from L equals to 1 to 2k minus 1 of L. And again, this is an arithmetic progression, and we're just going to use the same tricks we used previously, where we say that if we are summing up L to n, which is equals to n over 2 times n plus 1, and we know here our n is 2 to the power k minus 1, and 2n plus 1 is going to be just 2k. And so we can see this and that goes, and so can cancel that to get a 2 here. So as we go ahead, we have 1 over 18 plus 11 over 36 plus 1 over 18, 2i plus 2 times 1 over 3 to the power k times 2 to the power k minus 1. So we can now reorganize this a little bit so that we have a geometric series. So this is 2 times 2 over k to the power k over 3 to the power k minus 1 over 3. So this is a geometric series with initial value 2 over 3 and common ratio 2 over 3. Again, geometric series, initial value 1 over 3, common ratio 1 over 3. And so we can now sum that up. 2 over 3 divided by 1 minus 2 over 3 minus 1 over 3 divided by 1 minus 1 over 3. So this cancels with this cancels with this. And so we have 1 over 18 plus 11 over 36 plus 1 over 18, brackets 2i plus 2 times 2 minus a half. This is 3 over 2, so this essentially just becomes 3. So we have 1 over 18, 2i, this and that cancels obviously, and we have 2i plus 3. And then we have the integral from 0 to 1 of 1. So this is the same as just x with lower limit 0 and 1. So 1 minus 0 is just 1. So we have 2i plus 3 plus 4 in there, right? And so we can now reorganize this. So this is the same as 1 over 18 plus 11 over 36 plus 1 over 9i plus 3 over 18 is 1 over 6. 4 over 18 is 2 over 9. So if we transfer that this side, we get 8 over 9i is equals to 1 over 18 plus 11 over 36 plus a 6 plus 2 over 9. And so lowest common multiple is 36. 36 divided by 18 is equals to 2. 36 divided by 36 is 1 times 11, 11. 36 divided by 6 is 6 times 1 is 6. 6 divided by 9 is 4. 4 times 2 is 8. So 2 plus 11 is 13. 13 plus 6 is 19. 19 plus 8 is 27. So we get that 8 over 9i is equals to 27 over 36. Now multiply both sides by 9 over 8. We have I equals to 27 over 36 times 9 over 8. This goes to 4. And so I, which is our integral, is 27 over 4 times 1 over 8, which is now 27 over 32. And this is our final answer. So this it's been quite a process. I have enjoyed really solving this problem. I hope you do enjoy following through as well. If you have any questions, and you need help at any point in this problem, please feel free to share your question in the comment section. But it's been an absolute pleasure solving this problem. And yeah, if you've not subscribed to our channel, we do really encourage you to subscribe to our channel. And if you need to receive regular notifications once we come up with solutions, please press on notification bell. Better than that, thank you so much for your support. We look forward to sharing with you our next problem. Until next time, toodaloo, à la prochaine fois.